Hello everybody and welcome back to the Pie Show. We're on episode 4 today, which is Sources and Sinks. It's the last episode of season 1. Season 2 is going to start in a little bit and I'm not even going to give it away until then. We're on episode 4 now, which is about bright objects that convert matter into energy and dark objects that absorb energy and produce matter. Alright, so to put this more simply, part 1 is going to be about stars and what they do in their lifetime and what happens when they die. Part 2 is going to be about black holes and what black holes do in their lifetime and what happens when they die. And then we're going to have a part 3, and part 3 is going to be a hypothetical that involves aliens traveling faster than the speed of light around black holes. So here we are in part 1, and this part is about stars. And stars are essentially nuclear fusion reactors. So when a star is born, we have what happens is you get a large amount of hydrogen that all comes together, and the motion between the atoms speeds up, and I imagine this is likely due to friction. And then because they speed up, these atoms have chemical reactions that happen, also known as nuclear fusion, and this is what brings a star to life. So in order for helium to be created and more dense elements, hydrogen has to bond with other hydrogens, right? And there's a limitation that nothing more dense than iron can be created within a star's fusion reactions. That happens when a star explodes. Now, the reason I was talking about hydrogen speeding up, right, is because in order for hydrogen to fuse with other hydrogen, it needs to be going very, very fast because of the strong force. The strong force is what keeps protons from touching other protons. They don't want to do that. Also, electrons will be resisting other electrons, and unless hydrogen's moving extremely fast, those things won't collide. They'll just kind of repel or whatever, and then, you know, like I was saying with friction, if they go past each other, I think it's possible for sort of not exactly them touching, but they would kind of build charge off each other by just getting close to each other. So hydrogen would not want to get close to each other, but if they go past each other, they might kind of push each other around with their, with the electromagnetic force. So like basically if these electrons or protons are getting close to each other, they'll get the force of magnetic repulsion, and that might speed them up. So it might not necessarily be friction that speeds them up, but it could be the electromagnetic force that does that. Alright, so now we have a star here. No, it looks kind of weird, but this is kind of like the internal motion of the atoms within the star, right? So like, if you have hydrogen, and it's moving around, let's say it started near the center of the star. So the center of the star is the hottest part of the star, and so it will cause the hydrogen to heat up and move towards the outside of the star. And then once it gets out towards the outside, the gravity of the star will pull it back into the center again. And this is another way for hydrogen to be, bonding with other hydrogens, is once it gets out, once it falls back in, it might fall back in with another atom, and we could create deuterium, because the hydrogen will bond with the other hydrogen when they hit each other. They smash each other really fast in the center of the star. And deuterium is an isotope of hydrogen, right, which takes 2 hydrogens to make. And as you see, we go from having 2 protons and 2 electrons to having 1 proton, 1 neutron, and 1 electron. And that is because when hydrogen bonds with other hydrogen, 1 proton gets converted into a neutron and a positron, as well as a neutrino. Now, a neutron can chill with a proton, and positrons will cancel out. So that's why you only have 1 electron, because a positron is the antimatter form of an electron. And when matter and antimatter combine, you get a large release of energy. And that's how matter is converted into energy within a star. Also, neutrinos are really cool. They are everywhere, and they travel through our bodies. Like 1 billion or 1 trillion of them per second travel through your body, and you don't even feel them because they just have very little physical interactions with us. And anyway, as I was talking about hydrogen making deuterium, if two deuteriums come together, we get a helium. And that's how helium and more dense elements are made, is through nuclear fusion. Atoms coming together, and basically the speed of the atom being enough to beat the strong force. And then also on this side, we can make tritium through having three hydrogens come together, and they make two neutrons from their protons, which gets rid of these two electrons, so they keep this one proton and electron. Forgot to put a little minus sign there. And then you got another hydrogen here that will combine with tritium to make helium in a similar manner that two deuteriums would make a helium. Alright, now if we think about a star's death, this happens when a protostar, so a protostar is like the first stage of a star's life. That's just what we call it. And I think it's like the first 1.5 million or like 15 million years of a star's life. We just call it a protostar because it hasn't been categorized in one of these other ways as of yet. Now, basically there's like a mass scale here, but it's just, I'm not showing it, but the lower mass starts up here and then higher mass as you go down and towards the left like that. So a very low mass star would be less active because there's less matter to react, and we call these stars dwarfs. And now dwarfs can explode, and that could be the end of their life. They can also, protostar can become a giant if it's more massive, and this is what happens. It'll just expand. Its volume will increase quite a bit, and that's why we call them giants. And then they can shed their massive amount of volume and become dwarfs. They can explode, or they can implode, and all that volume will get sucked back up into itself and it'll become a neutron star. Protostar could also implode right away. If it's like really, really massive and it's living very quickly, it'll become a neutron star. And neutron stars spin very rapidly because of the conservation of angular momentum. And neutron stars can also explode, or they could become black holes. That's a possibility. Protostars can also go straight into being black holes, but they gotta gain mass very, very quickly to do that. And then they also would have to implode. And that's how black holes are created, is from an imploding, very large, massive body. Because that's how a black hole is the concept of just having extremely high gravity in a very small location. So it has to be a very, very dense object in order to make a black hole. And a black hole, I don't think a black hole will ever explode, but we'll talk about black holes in part 2. Alright guys, so we're on part 2 now. This part is about black holes, and black holes are kind of like extremely powerful and mysterious spherical whirlpools. And so in this part I'm going to be filling up my sink to represent the universe. And you can think of the faucet head as a star pouring light into the universe. And then we're going to remove the thing that's clogging the sink to have it represent a black hole. And we're going to get a whirlpool going. Alright, so as we were talking about in part 1, black holes are created by a star that becomes extremely massive and then it implodes or it collapses in on itself. And this is because when a star does this, the matter it keeps is the same when it collapses in on itself, but its volume decreases, which makes it, that's what makes it so dense. And when an object does this, it makes it so other objects that come near it, like light, for example, will be able to be consumed by that object. As when before, when it was a star and it had a lot of volume, it would even emit light itself, and light couldn't get swallowed up by it because it was large enough of an object that it would bounce off the object before it would get close enough to get absorbed by it. Alright, so as it turns out, black holes are fairly simple. There's really not a lot to them. In general, there is the event horizon, which is this glow stick that I'm holding to the bottom because it floats. And with the event horizon, if light were to enter within this circle, which is the event horizon, then it would be absorbed by the black hole and it would never come out again. And this is because the gravitational pull of the black hole is so incredibly powerful that even the speed of light isn't fast enough to escape. Now, what happens when light goes in there is light's kind of like thought of as a form of energy, and when it gets all pushed into the same point, which is the center of the black hole, then what I think happens is it just adds to the mass of the black hole. So you would be converting energy into matter within the black hole. Also, there are gases around the event horizon that will be getting sucked in by the black hole, and light could be bouncing off of that gas, and we call that stuff the accretion disk. It's just something that's kind of visible. That's how we were able to get a picture of a black hole. Alright, so imagine for me, if you will, a universe that has no black holes, and it just has stars, and these stars are just creating light just a ton of light, and they're converting all the matter into energy, and that energy is light. Now, if this was our universe, I don't believe that we'd really be able to see very much, because there'd be so much light that it would be overdoing our eyes, and we'd have to be able to adapt as we live to be able to see in a universe of just so much light. And then if we were to create a black hole by getting rid of this little hand towel that's covering up the sink hole, then we're going to see what would happen. You know, we're going to see the whirlpool. Is it working? Hey, go, go, go. There we go, I got a little one. Yeah, this isn't the best sink for it. But as you can see, it's being pulled down in the center there. And when it gets pulled down like that, that's what happens to the energy. And in that little point in the middle, that's where all the matter goes. And it gets crunched really hard, and then the black hole will actually grow in size, and the event horizon will increase its radius, but this happens very, very, very slowly. Alright, so that's the stuff that a black hole does in its lifetime, and in its death, it does something else, and I will try my best to show you what that is. We've seen this happen a number of times in distant galaxies, and there's a name for a dead black hole, or like what happens to a black hole when it dies, and it's the word quasar. So a quasar is like basically what a black hole does when it dies. It just looks kind of like this. It's just like if you had like, you know, if this was a spiral galaxy going around and the black hole was to be in its death process, it would look like this. It would shoot light up and down vertically, and then the rest of the galaxy would be spinning around that pretty much. I don't really know what happens after that, because, you know, I don't think anybody really does at this point. But yeah, it kind of like explodes light in a vertical fashion. And I don't know if this is what happens with other types of galaxies, like a cluster galaxy. Those ones kind of baffle me a little bit in general. But I imagine it would do a similar type thing. It might even shoot light out in more of a explosive kind of fashion, where it's just all outward instead of vertical like that. But yeah, check out quasars if you don't know much about them and you want to learn more. Alright everybody, welcome back. We're on part 3, which is about aliens and hypotheticals. It's always my favorite part of every episode. So first, just wanted to give a brief definition of spaghettification. This is when there is a long stretching of a physical object due to an immense gravitational field. So this definitely happens in black holes if it happens anywhere. Anyway, so we're going to start with this radius. I looked online and kind of found this as to be pretty close to the radius of the Earth. The Earth is not exactly spherical. It's like pretty close. It's kind of more like elliptical in a sense. But yeah, so this is like pretty close to what would be the Earth's spherical radius. And so if we plug that into our escape velocity equation and solve for the mass, and if we plug in, so this is the escape velocity equation, is v equals the square root of 2gm over r, where g is the gravitational constant. We're going to use, for the velocity, we're going to use the speed of light, which is c, because we're assuming this is like a event horizon. And so if we square both sides, multiply r onto the other side, we got r v squared equals 2gm. eventually we get to the point where we got mass on its own here. We have all the other variables accounted for, solved for. We get this big old mass, which is about 1,000 times the mass of our sun, and this will be the mass of our black hole. Alright, so the next thing here is we got this volume here, and this volume is with the radius of our close to Earth's radius. So this is pretty much going to be what would be the volume of an object if it were to be in the space of the event horizon of this black hole. And in which case I wanted to mention that this volume, in order for us to actually truly have a black hole, it is necessary that this volume be greater than the volume of the actual black hole mass. And this is because if this wasn't true, and I'm just going to go ahead and show you what I'm talking about here. So this is kind of what I've drawn out. We got our event horizon here and our black hole mass, which is within that. And if our black hole mass was any bigger than this event horizon, then we would not have an event horizon, because light would simply bounce off this object before it gets absorbed within the event horizon. So it's necessary that the black hole mass have a lesser volume than the volume of this empty space. Yeah. Also, speaking of volume, real quick, just wanted to point out that the reason we have black holes that are a possibility is because of density, which is mass over volume. So in order to have a black hole, we must have a very dense object, which means you got to have a lot of mass and a very small amount of volume to have a high density, which is what makes a black hole what it is. And then if we continue on from where we were, so this is why I have this equation here, the radius over 4. I'm making this to be the volume of the black hole mass. So we're using this radius to be the radius of the black hole mass. That's why it's the radius of what we had, approximately the Earth, over 4, so that it looks about a quarter of the size of the event horizon. And we come out and we get this volume here, right? This would be the volume of, right, this is the volume of the black hole mass, which is less than the volume of the empty space for the event horizon. And then lastly, I solved for, if I use r over 3 instead of r over 4, this can give us these points right here, which this is the speed you'd have to be going to be within the event horizon, but without getting stuck within it. And so this is greater than the speed of light, of course, because we're within the event horizon, and it's about 49 over 40 times c, which is like, you know, a little bit more than the speed of light, but it's not even 1.5 times the speed of light, which is why we're going to use 1.5 times the speed of light to go around here, and we're going to have like an alien spacecraft. Hypothetically, we're going to have an alien spacecraft. It's going to come in from one side. It's going to shoot through and just check out that area there. Right, it's going to be real close to the black hole mass. And this is just, we're thinking this is like an alien spacecraft somehow knows how to not become spaghettified by the mass of the black hole. And they're just going to check out what's going on within the event horizon because they're curious. That's the hypothetical we're going through here. Alright, so because of having this capability, if an alien could travel over the speed of light and they could avoid spaghettification, we could find out about how long they'd have to look while they're within this event horizon, right? By using one of the simplest equations, velocity equals distance over time. Now, so our velocity here, as I've said, is 1.5 times c. So we could say 1.5 times c is going to be equal to the distance, which is about 2 times this radius, also diameter, so it's another good use of the letter d. So let's say 2 times 6.371, 10 to the 6th. Okay, and then that's going to be over our time. We're going to solve for our time, so we multiply by time, divide by speed. We get our final value, which I will use a calculator to solve for. Alright, so I just got done using my calculator to find the answer to this. We got answer of 0.028 seconds. So this should be three hundredths of a second. About 300ths of a second is how long it would take for an alien to go through this event horizon of this black hole. Not a very long time to look around, and also, interestingly enough, I can say with a good amount of certainty that I don't think, even being this close to the black hole mass, that an alien could even see the black hole itself. Because the light coming down would kind of be spiraling in, kind of like we were doing with part 2 with the water going down the sink. So it's kind of crazy to think, but they could, likely while they're within this black hole's event horizon, they could see outside of the black hole, and while they're within the black hole, nothing could see them. So that's interesting to me. Also, I was thinking a really cool hypothetical, which kind of ties back into episode 1, would be that if an alien was in a spaceship flying into a black hole and they want to come in, check it out for a minute, and then come back out and return the way they came. If, as they were on their way heading in, if they're traveling faster than the speed of light, they could say hi and wave to their future self that they know is going to come out of the other side of the black hole. And then when they're back returning, they could look at the image of themselves waving from the past, and they could wave back again and say hello to their past self from the point after they had exited the event horizon of the black hole. And to me, I think if I were to do those things, I would feel very giddy, and I would think that's really cool. Also, I don't know whether or not I'd really want to do this trip through the event horizon of a black hole, because you have such a short time to check it out that it's kind of sad. It's like, what is the point of even going through if you blink and you could have missed it? Alright everyone, so thank you for watching my episode, the last episode of the season. I hope I got the point across that this episode was about the fact that stars are a source for energy and a sink for matter, as well as the contrary is true for black holes, that black holes are a source for matter and a sink for energy. I hope that you enjoyed watching, and I hope you feel like maybe either you learned something or I helped you, open your mind up to a different way of thinking about stars and black holes. And, for those of you who celebrate Christmas, Merry Christmas. This is my little Christmas tree. It's that time of year. If you don't celebrate Christmas, happy holidays, or, sorry I brought it up, I guess. Thank you again for watching. You guys are beautiful, and I love you. And check out season 2 when it comes out. Probably be happening sometime around March of next year. Happy New Year.